Let's calculate the enthalpy change when hydrogen peroxide decomposes into water and oxygen. Hydrogen peroxide breaks down into water and oxygen gas in this decomposition reaction. First, let's look at our balanced chemical equation. 2 molecules of hydrogen peroxide decompose to form 2 molecules of water and 1 molecule of oxygen gas. To calculate the enthalpy change, we need the standard enthalpies of formation for each compound involved. Let's identify the standard enthalpies of formation we'll need. Here are our standard enthalpies of formation. Hydrogen peroxide liquid is negative 187.8 kilojoules per mole. Water liquid is negative 285.8 kilojoules per mole. And oxygen gas is 0 because it's an element in its standard state. Remember, elements in their standard state, like oxygen gas, have 0 enthalpy of formation by definition. Now let's apply the formula for calculating enthalpy change of reaction. The enthalpy change of reaction equals the sum of enthalpies of formation of products minus the sum of enthalpies of formation of reactants. We calculate the energy of products and subtract the energy of reactants to find the total energy change. Let's calculate the enthalpy contribution from the products first. The products side has 2 moles of water and 1 mole of oxygen. Substituting values. 2 times negative 285.8 plus 1 times 0. That gives us negative 571.6 plus 0. So the products contribute negative 571.6 kilojoules. Now let's calculate the enthalpy contribution from the reactants. The reactant side has 2 moles of hydrogen peroxide. That's 2 times negative 187.8, which equals negative 375.6 kilojoules. Now we can calculate the final enthalpy change. Delta H reaction equals negative 571.6 minus negative 375.6, which becomes negative 571.6 plus 375.6. This gives us negative 196.0 kilojoules. The energy diagram shows products are lowering energy than reactants by 196 kilojoules, indicating an exothermic reaction. Let's interpret what this negative enthalpy change means. A negative delta H of 196 kilojoules means this reaction is exothermic, releasing energy. Specifically, 196 kilojoules of energy is released for every 2 moles of hydrogen peroxide that decompose. This significant energy release explains why hydrogen peroxide decomposition can be violent and is sometimes used in rocket propulsion. The reaction releases heat energy to the surroundings, which is characteristic of exothermic processes. Let's summarize our calculation of enthalpy change for hydrogen peroxide decomposition. For the decomposition of 2 moles of hydrogen peroxide into water and oxygen, the enthalpy change is negative 196.0 kilojoules. This means the reaction releases 196 kilojoules of energy as heat to the surroundings. The products are more stable than the reactants by 196 kilojoules, which drives the reaction forward spontaneously.